Hi, good afternoon, and welcome to my session where I'm going to talk you through using HTTP in .NET Core applications. My name's Steve Gordon. I'm a Microsoft MVP, Pluralsight author, and senior engineer at Elastic. You can find me online. I'm at Steve J. Gordon on Twitter, and I blog regularly at stevejgordon.co.uk, where a lot of the topics that I'm going to talk about today will be expanded upon if you want a little bit more detail. We've got a lot I want to pack into the session, so I think it's best that we just dive straight in and talk about what we're going to cover today. So what I want to show you is kind of the evolution of using HTTP and HTTP client in .NET Core and some of the challenges you may run into and how to work around them. And as we go, we'll talk about a feature called iHTTP Client Factory that can kind of help you with some of those challenges. We'll talk a little bit about outgoing middleware. So this is the idea of cross-cutting concerns that we may have on outbound HTTP requests. We'll talk about some patterns and recommendations that you can apply when you're working with HTTP client. And we'll wrap up at the end by just kind of reviewing some of the things that have happened since .NET Core 2.1 really, all the way through to .NET 5. So some of the key improvements that are being made there. We're going to start with this code. This code is just an example code that we're actually going to improve quite a bit as we go through the session. So this is our starting point before we refactor it and improve it. It's basically assuming that we're inside an ASP.NET Core application. So we're inside a controller. We have an action method that's going to handle requests into our API. As a result of a request coming into us, what we're actually going to do is communicate downstream to the GitHub API to get some data. And that's what this code is doing. Now, one of the first problems with this code that I want to draw your attention to is this using block here. What we're doing is when a new request comes in, we create a HTTP client, we use it to make our request to GitHub, and then when this method exits, the using block will dispose of the HTTP client. And this seems reasonable. HTTP client implements iDisposable, and one of the design patterns in .NET is that when you're using something that's iDisposable, it may have unmanaged resources that need to be cleaned up, and as a result, we should you put it in a using block or manually dispose of it. The problem is with HTTP client, it's the chain below it, the HTTP message handler chain, that is actually responsible for the unmanaged resource, and it's that's iDisposable. As a result, HTTP client is iDisposable. And what's at the end of that chain is ultimately a network socket that's been opened to do the outbound HTTP request. So with this code as it stands, what's happening is every time someone makes a request to us, we open a new socket because we've created a new HTTP client and handler chain, and then we communicate over that socket. And as soon as we've finished, we then dispose. And as part of a disposal, the socket will be closed. And this seems like it might be okay, but there's two main problems with this. The first is around the potential risk for socket exhaustion. So although we are done with the socket and we've closed it, the way that TCP works is that there's a period of time called the time wait period that those TCP connections, the sockets that were being used, go into. And that state means that for around 240 seconds on Windows, at least, they can't be reused by any other process. So whatever port we used for our outbound connection is kind of reserved for that period of time. And the challenge there then is if we have enough requests coming into our application, or we're making enough calls in some kind of tight loop, and opening and closing these sockets, we can end up where nearly all of the ephemeral ports available on our machine are tied up in this time wait period. And what that means is ultimately we could run out of available ports and we won't be able to start any new requests. And that could be a serious problem for an application. There is also a bit of a performance overhead in continually opening and closing connections. Every time we open a connection, we have to do a TCP handshake, potentially negotiate for TLS as well. So this is overhead that we can avoid if we were to reuse the connections for a period of time. To just show you what this looks like, I've taken the code that I had there and run it in a tight loop of 20 iterations. And as you can see, after every iteration, because it's disposing of the client, we're putting the port that we were using into this time wait period. You can see all of these outbound ports on the left are open to the same remote IP address for the communication, and they're all stuck in this time wait period now. And that's 20 in that short period of time that I tied up. So the first thing that comes to mind then is, what do we do about this? What's the solution? And pre.NET Core 2.1, there was only one good solution, which I'll show you. Since 2.1 of .NET Core, a few things have happened that we'll talk about as we go through that make the process easier. So the simple solution pre.NET Core 2.1 would be that we would reuse the HTTP client. And one way we could achieve this in a very low-tech way is to register it inside the configure services method of this startup class. So this is where we build up our DI container. So in here, if I were to create a singleton registration for HTTP client, I can now retrieve that same instance, which uses the same handler chain and therefore the same connections at the end of it for the lifetime of the application. And then to use this in my controller, I'd simply inject my HTTP client that will be resolved from the container, always being the same instance. And then in my code, I could use that client. This means I can get rid of the using block, but it does leave me with one small challenge. What do we do about these client-based configurations? So HTTP client is a thread-safe type from the perspective of its methods, but its properties are not. And what this means here is we're mutating this default request headers by adding new headers into it. Well, other threads might be sharing this same HTTP client for other requests in our application. And we could run into a situation where we end up with, the wrong headers going out on the wrong request, and that would mean not ideal. So to work around that for now, what I'm going to do is set them at the per request level. And the only downside of that is that obviously for every request, you have to remember to add these on. Otherwise, you won't authenticate with the API that you're trying to talk to. And then finally, we can update this code here to use the injected client. So this all seems well and good, but unfortunately, there is a little downside, particularly in .NET Core 2.1 and earlier. And the issue in that situation is DNS. So what we've done there is we've reused the HTTP client, we've reused the handler chains, we've reused the sockets. Those sockets, when we first make a connection to, some API.com, there has to be a DNS lookup to find out what server to communicate with. And if we keep those sockets open for a long period of time, it's possible that they will be talking to an outdated server. So often, particularly in sort of microservices and cloud-based environments, services change IP address fairly often, and DNS is updated to kind of handle that situation. So what we ideally want to do is respect the DNS time to live and make sure that our connections don't outlive that TTL so that we get updated information when it's applicable. And by using the singleton HTTP client, unfortunately, we're not really achieving that. So there is a risk that we're trying to send requests to something that's no longer there, or maybe in a blue-green deployment, they've switched what is actually production and we're talking to the outdated version of the site or the API. Not great. Now, since 2.1, there's been two kind of ways that this has been fixed, and we'll talk about both of them. I'm going to start with HTTP Client Factory because this one not only solves that problem to a degree, but it also provides some other functionality that I think makes it sort of stand out even without the solving of the DNS issue. So what the Client Factory does is it manages the lifetime of those message handlers. So the message handlers, remember, are the thing that hold on to the connections and the connection pool. So it's going to manage that handler chain for us so that they live for, by default, 2 minutes, and then they get expired and then new handler chains get used. So the factory will always return us a new HTTP client instance, and it will use either a new or existing handler chain, depending on whether those have expired or not. And this is how, by cycling those handler chains, we assure that we reuse the connections for, by default, that 2 minutes period, but we do let them be refreshed periodically so that they pick up those DNS changes. On top of that, it provides a central location for naming and configuring logical clients, and we'll talk about how that works shortly. It helps codify the concept of the outgoing middleware concepts that we'll talk about as well. And it also even integrates with Polly, which is this third-party library that we can use for transient fault handling. So let's convert our code. What we'll do first is we'll do the minimum thing possible. So what we'll do is just see what's the smallest change we can make to add the client factory in. And the first change we'll make is we'll get rid of the singleton registration in services there, sorry. And we will then add HTTP client. This is a helper extension method available in the Microsoft.extensions.http NuGet package, which is included for you by default in ASP.NET Core 2.1 and above. And this registers that client factory feature. Once that's registered, we can inject into our controller an iHTTP client factory. And from that point, we have this thing that can give us these client instances that we need and manage the handler chains and connections on our behalf. So this means in this code, what we can do is update it. So we call create client on the factory. Once we've got our instance, we use it just like a transient type. We just use it for as long as we need it and let it be garbage collected when we're done. That's all okay because the handler chain is the key piece that's being managed for us. The HTTP clients are just transient instances now. Now, I said that we could use these for the logical client concepts, and one of those ways is by using named clients. So let's amend our code here, and what I'm going to do is define a named client. So this client is named GitHub. This string here defines our name, and then we can provide this optional configuration delegate, which is for every new HTTP client that the factory produces, it's going to run it through this delegate before it hands it back to us from that create client method. So we can do things in here like set the base address and the default headers, because we know that in theory, we shouldn't be sharing that HTTP client around anymore. It's our own instance every time we ask for one from the factory. And so now it's kind of safe to use these configuration values earlier. And what this means is we have a single place to register all of these settings. So now in my controller, I don't need the full URL because I've set a base address. I just need the path. I don't need to set the request headers at all. And the only change here is that we then need to ask for the client from by its name. So here we're saying we want the GitHub configured client. Great. We can take this a step further, and this is kind of where I prefer to use the feature is with typed clients. With a typed client, we create a class that represents essentially an abstraction around the endpoint that we're talking to. So here I have a class, it's called GitHub client. I have an interface for it that I've defined. It doesn't have to use an interface. And the only real thing that it must do is it must, as one of its arguments, accept HTTP client. The other things can be resolved from DI as well. So if you have other services you want it to use, that's perfectly fine. But it must accept HTTP client because the client factory will hook in here and provide the actual client. Now we have the option of configuring the client here in the controller, which is what I'm doing for this example. We could still use a delegate-based approach when we register it. But now that we've got this thing that represents talking to GitHub, I'm just going to reuse that context and apply everything in this single responsibility. In here, we can define a method, and this could be one or more methods that talk to the external API. So we've wrapped inside an abstraction in our application code this concept of, okay, well, we want to get the repositories for ASP.NET Core. So we've got a method that we could call on our client to do that, the implementation of which is now kept in here. So this implementation is basically what we just saw. Now, to register this, we can register multiple named clients. We can register a combination of typed clients and named clients. Just for fitting it on the screen, I'm going to get rid of the named client and register my typed client instead. And all it means we have to do is provide one or two generic arguments. Here I'm providing an interface and the implementation. You could just provide an implementation if you're not using interfaces. But the interface is nice because it means everything's much more testable later on. So now this is registered, we can update our controller. And in our controller, instead of accepting an iHTTP client factory, what we now accept is an iGitHub client. And this gives us a little bit more clarity, I think, if you look at the signature for the constructor as to what type of work this controller might be doing. This means that we can now dramatically reduce our method call here because all of this code doesn't really, in my opinion, belong to a controller. Controllers are responsible for sort of request handling and, basically being the point where requests get routed to kind of trigger application logic. But burying all of this stuff about dealing with external HTTP inside the controller means it gets quite bloated. But because we've now moved that logic into the client, the typed client, we now get a much more reduced controller and one that's easier to test because we could easily mock the iGitHub client for different responses it might give us and validate that the output we expect is returned from the controller. So in this case, we just call down to the GitHub client. We call our well-named method that describes the action we're taking, and we get back the data that we need. Now, I said earlier, we talk a little bit about outgoing middleware. So outgoing middleware is very similar to ASP.NET Core middleware for incoming requests that you may have built middleware pipelines for. What that allows you to do is to handle cross-cutting concerns as requests come in. With outgoing middleware, it's the same idea, but it's now for the outbound calls. So logically, this is what it looks like from a sort of high-level perspective. We make a request to HTTP client, it goes out to the internet, and it comes back. Simple. But what's actually happening under this sort of layering here is that we have this HTTP message handler chain, and that's responsible for forming the actual HTTP request and opening the network connection and using sockets to actually send the request. And there's multiple layers to this. I've shown two in here, but actually there's often quite a high level of chaining here for all sorts of functionality like applying proxy settings and things. But what this means is once we've got this message handler chain, we can add our own handlers into that chain. And these run before the kind of system level handlers, but they give us the power to provide any cross-cutting concerns that we may have for our application as well. So perhaps you want to do some validation before requests go out. Perhaps you want to do some additional header manipulation or some kind of cache control on the responses. Or maybe you want to talk to an external OpenID Connect server to get a token and apply it to the requests on the way out. All of that is possible with these kind of cross-cutting concerns of handlers. Now, to create a handler is pretty simple. We create a class that derives from the delegating handler base class, and we're going to implement one key method there, but we can also, if we're using iHTTP Client Factory, we can use injected services as well. So here I'm injecting an iMonitoring service that we'll use in a moment. To actually implement this, what we need to do is override the send async method. And this is what gets called as the handler chain kind of gets executed. And it gives us the opportunity to do a couple of things. Before the request is sent, we're not doing it here, but before the request is sent, we could manipulate it, add headers, even short circuit this pipeline and not even send a real HTTP request. Maybe we go to a cache. In this example, what we're doing is we're calling base.sendAsync, which calls the next handler in the chain. Once that's eventually got a response, it's going to pass it back to us. And before we pass it back up the rest of the chain, what we're going to do here is use the monitoring service to record a metric. And we're just going to say, here's the status code we got. So this is a cross-cutting concern that could be really useful because we could monitor the status codes we're getting back. And if suddenly we start getting 400s or 500s in much higher volumes than we're expecting, we can, of course, kind of correct that and alert on it. So once we've got this delegating handler, we need to register it. And with the factory, that's really easy. Once we call add HTTP client, we get back a HTTP client builder. And on there, we can chain fluent methods for configuring that instance. So here we're adding the message handler, and we could add one or more of these if we want to. So we add our message handler by name. And the only other thing we must do is remember to register this as a transient service as well within the DI container, which we're doing in this line. That's pretty much all there is to registering these middleware components. I'm going to jump on now and just briefly touch on Polly. I'd like to talk about it a little bit more, but it's a topic that's really quite deep and probably a whole session of its own. What Polly is it's a third-party open source library for resilience and transient fault handling. So if you think of HTTP, we're going over a network connection, we're talking to external services, there's many things that can go wrong. The network can get interrupted, the server can be unavailable, can have a glitch, and that means that some of our requests might time out or may fail completely. In those situations, it's good if you write code to handle that. You don't really want to pass those errors on to your own consumers if you can avoid it. And Polly provides this concept of policies that we can configure to handle any kind of error situation. It's not limited to HTTP at all, but it works very well there. So this might be things like, well, maybe if the request fails, we'll retry it up to a certain number of times, or after a certain period of time, we just time out. We can add other things like circuit breakers and bulkhead isolation that provide the ability to avoid cascading failures. And that's particularly useful in microservice environments where you might have service A calling B, calling C, calling D, and you don't want failures in one of those to affect the others. We can handle all of that by building quite complex policies if we need to. So let's have a look at a really simple one. What we want to do is we want to add retry to our external calls to GitHub. To achieve that, we can add the transient HTTP error policy here onto our request. This is another helper method that is available. We have to bring in an additional package for this from the Microsoft extensions.http.poly so that we can actually use that. And once we get that, we get back this builder, which is a delegate that we can use to configure what happens for any kind of transient errors. And transient errors in the context here are automatically going to be things like 429s and timeouts and request exceptions. We can then decide what we do in those situations. So here I'm applying a wait and retry. I'm saying I want it to wait and retry up to 3 times, and my retry period is going to exponentially back off. So each attempt we make is going to wait a little longer before it tries again. And this gives the downstream service more and more time to recover. And that's all there is to it, to add a fairly simple retry policy using this integration. Now, before I conclude today, I want to run through some other things I see people doing wrong and some tips around how to avoid them. And the first of those is around response content allocations. So if we go back to our typed client here, and we can have a look at the code that we have, the lines I want to draw your attention to are at the bottom here. We're calling read as string async on the content. And what that's giving us back is a string that represents, in this case, the JSON that we've received. Because we've got JSON and we actually want a typed object, we're going to actually use, in this case, it's JSON.NET, but it could be the newer system text JSON or any other serializer. We're using that to deserialize from the JSON string into the object that we actually want. So that seems reasonable. The problem here is if you think about that string, we're just using that string as an intermediary object. It's a very transient object. It's used purely as a kind of a buffer between the content stream that we have on the response and JSON.NET. And this means we're allocating that string every time we deserialize. Now, if it's a small response, it might not be too bad, but for larger responses or things that are happening very often, that's a lot of strings we're allocating unnecessarily. And these all add up to, memory pressure that might result in garbage collections. It's also a possible attack vector. Someone could maliciously send you a very large response. And if you try and read that entire response into a string in memory, it could very quickly cripple your machine in terms of how much memory it has available. But JSON.NET and even things like system text JSON, they all support working with deserialization from streams, and it's much better to use that rather than just converting to a string on the way in. So we can use this read as async method here from Microsoft.ASP.NET.WebAPI.client, which is another package you can bring in, or it's included in most ASP.NET Core solutions for you. What this provides is this kind of helper method that says, okay, I just provide this, the type that I want, and behind the scenes, it's going to use the streaming API and actually use Newtonsoft JSON as was intended without creating that intermediate type. So all we're allocating is the final object that we want from the deserialization. And if you're using system text JSON, it's as easy because they have APIs that you can call that directly deserialize from a stream, and that's the right choice there too. So this will give you better performance in many situations where you've got higher load or bigger responses. The other thing I want to touch on is handling errors. And we talked about errors in the sense of transient HTTP errors, but what about errors that aren't a networking or communications issue, but are just that the server's returned a 400 or a 404 or some other status code that represents an error? What do we do with those? Well, at the moment in this code, what we're not doing is checking before we read the content that we've got a valid response. And what this could mean is that we could get an exception thrown. If we got back a 404 with no content, this content call to try and deserialize might result in an exception being thrown. So what we should always do as good citizens is make sure that when we get a response, we first check if it's successful. And we can use the ensure success status code as a shorthand way of doing this. And what this will do is throw an exception if the code isn't in the 200 range. And so this means your consumer would have to catch that exception and handle it. But at least it means we're not reading the content and getting some unexpected exception. If you prefer, and quite often this is easier to kind of reason about, is that we can actually just handle it in code. So we can say response is success status code, gives us a Boolean. And if it's successful, then we're going to return the deserialized content. Otherwise, we're going to return an empty array, so some kind of default object. This is a reasonable way to go. Other things you might want to do is also check that you do actually have content before you read from it. I haven't got that here for brevity, but don't just assume because you've got a 200, it might, they may not have sent you any actual body in that response. So things to consider there before you deserialize or read the content. Another thing I want to touch on is this idea of handling cancellation. So this is another way to avoid workload in your system that you don't want to be doing. So if we look at our HTTP client, typed client here, we're taking this request that we're sending asynchronously, but we've not got any way to cancel that out. And with tasks and async, the good practice is to use the cancellation token concept as a way of avoiding doing work when someone no longer needs it. So what we're going to do is accept an optional cancellation token into our method. Before we even send the request, we'll call cancellation token.throw if cancellation requested. So this is the kind of cooperative cancellation approach. And what we're saying here is this will throw an operation cancelled exception if the cancellation token has been signaled. and we won't even try and send the request. So this could potentially avoid us even doing the work to open a network connection. Now, chances are people won't cancel that quickly. So what we're going to do is also pass this token down to send async and read as async as well. These will also cooperatively cancel at the appropriate places. All of this is about stopping work that might have, CPU work or, memory pressure on our system if someone no longer requires it. Now, how are we going to signal the cancellation? Well, in this case, we're using ASP.NET Core, and we've got a controller and an action that's invoking this typed client. Now, a little known fact about ASP.NET Core is that we can actually inject a cancellation token into our action method here. So we can accept cancellation token, and what will happen is when ASP.NET Core activates this controller and invokes the action method, it will pass in a cancellation token if we ask for one that's tied to the current request. And this means if the consumer of our API cancels or times out or gives up in some way that we can pick up, then this cancellation token will be cancelled. And that means that we can then pass that down in this code here and stop doing work. So if the consumer of our API has gone, we don't need to call GitHub to get any data for them or deserialize it because there's no point. Another thing I want to touch on is HTTP completion option. This is kind of a high performance option that you may want to consider. So what happens by default is when HTTP client calls send async, the response comes in and it gets pre-buffered into a memory stream. And the reason that happens is so that as soon as it's buffered the entire response content, that socket can be released back into the pool so that the next request that needs to make an external call can use it. So this optimizes our usage of sockets. One disadvantage, though, is that pre-buffering. So if we might want to conditionally do something with this request based on the headers alone, we could actually ask for HTTP completion option response headers read, which means this awaitable method here returns with a response as soon as the headers are available. At that point, we can inspect the headers and we can choose whether or not we even read that content. And this might be optimizing situations where you have large payloads that would still be streaming in at this point. Now, this does have a bit of a side effect in that we're now tying up that socket because we're saying, actually, no, we're in charge of streaming off of the socket that we're using. So we can't release it back to the pool until we're done with it. And the way we signal that is by using dispose on the HTTP response message. So the right way to apply this is with a try finally. So whatever happens in the try, we make sure at the end we do dispose of the response. And this is the one situation where you might want to dispose of a HTTP response message today. And this works fine for those, as I say, high performance scenarios or cases where you conditionally read the content based on certain headers being available. You might not need to do the content read at all, and you can short circuit that. This all leads us to a common question: when should you dispose of these things? Because disposal is complex in HTTP client, at least. The answer is, unfortunately, it depends, but I'm going to try and summarize the options. If you're using HTTP client factory, then disposing of the HTTP client has no effect, has no harm, but that HTTP client is intended to be a transient object. The factory is managing the actual disposable resource, the handler chain and connections, separately. So you can dispose of it or not dispose of it safely. If you're not using HTTP client factory, then generally you never want to dispose of HTTP client because you want to be reusing those connections. But as we talked about, you do need to think about the DNS refreshing, and we'll talk about how that can be corrected in another way in a moment. We can also dispose of the request message. Today, that only has effect if you set stream content on that request message. And what it's essentially doing is once the request is sent, it's disposing of that stream for you. You may or may not want that behavior. That one's more up to you and your decision on whether that's right for your code. And for response, as I just shown, the only real time that at the moment with the current implementation is when we're using response headers read, that we need to dispose of it ourselves. Now, I said earlier that ASP.NET Core and HTTP Client Factory solved the problem of that DNS issue in 2.1. Well, actually, at the exact same time, the .NET team themselves have introduced this thing called Sockets HTTP Handler, which also solved the problem. So this is built on top of raw sockets. The difference being that before .NET Core 2.1, all of the HTTP code, the request and response handling, was managed through the underlying operating system library, so libcurl on Linux or WinHTTP on Windows. The disadvantage of that is, A, there were some performance differences between Linux and Windows. Linux was significantly slower. B, the behavior wasn't always consistent. And C, it meant that we had those issues around DNS and connection pooling. Well, now that everything's moved into managed code and built on top of raw sockets, the managed code can maintain its own connection pool, and it's recycling those connections based on configuration that we can control. And by default, the timeout is infinite, but you can set a setting if you want to just use connection pooling without having to use Client Factory. It's enabled by default in .NET Core 2.1, and even more recently in .NET 5, they've actually removed the old platform-based handlers. So it's now, a real first-class citizen in the code base because it's fully featured now. Now, I said that we could do connection pooling with that. This is similar to Service Point Manager, if you've ever used that in .NET Framework. And it allows us to configure the pooled connection lifetime. So how long should connections that are open from the pool be reused? And as I say, it's infinite by default, but you can configure it. We can also, as well as setting a max time for the connection, set an idle timeout as well. So for connections that aren't being used and haven't been used for some time, we could maybe close them earlier than ones that are actively being used. You can safely reuse the same HTTP client and the same handler chains without socket exhaustion or DNS concerns if you've configured these and you're using a newer HTTP client on 2.1 or later. So what else has happened? Well, in .NET Core 3.0 and 3.1, HTTP2 support was added, but it wasn't enabled by default because it was kind of primarily for gRPC scenarios. So it wasn't quite fully featured in terms of the full spec. So because of that, it's not enabled by default in 3.0 and 3.1, but you can configure it when you need it. And you can set a version property on the client itself or your request messages to say which version you want to use, and it will try and negotiate that version for you. In .NET 5, we've seen some further improvements to that, so it's now even more fully featured, which is why they've been able to remove the old platform handlers. They've added experimental support for HTTP3, which is quick. So this is a new kind of evolving standard that you might want to use in modern situations. They've improved how the exceptions work. So they've added some things like the status code now gets included on some of the exception messages, and some of those represent timeouts more accurately. They've added sync APIs. So you really don't want to be using the sync APIs unless you have to. But in situations where you do have sync code and you're kind of doing async over sync or sync over async situations, those get problematic. And so these sync APIs are there if you're in a synchronous code path already, rather than calling something like getaway to get result, which could be dangerous. You can end up with deadlocks. You can use the sync APIs, and those use the low level synchronous IO operations under the hood. They've also added some improved telemetry as well. So if you need to know how many request connections are being opened, how many DNS connections are happening, that kind of thing, you can do so. So I'm kind of near at the end of my time, and I want to leave a few minutes for questions. So let's briefly summarize. I do recommend people use or check out iHTTP Client Factory in .NET Core 2.1 and above. While connection pooling and the new sockets HTTP handler allow you to solve the DNS issue, HTTP Client Factory adds all of those other functionality in as well. So named and typed clients, and the idea of configuring, easily configuring delegating handlers, and doing things like integrating the poly, all make it really quite powerful. And if you're building kind of an API that needs to communicate with external services, it's a great way of adding that in a feature-rich way. If you are doing HTTP, think about transient issues. Poly is a great way of dealing with them. It's not the only way, but it avoids you writing a lot of boilerplate code yourself. Be aware of the content read as string async and get string async methods. Remember that you're allocating a string there. And if you don't need the string, but you actually just want a type, a strongly typed object, use the stream-based deserialization options that are available to you. Do expect and handle errors that might come back from the server itself, so not just transient errors. Do pass cancellation tokens, general good practice if you're using async APIs, pass the cancellation tokens that you have through so that work can be prevented if someone cancels upstream. Do dispose of appropriately. It's a little hard to know exactly when. Hopefully what I've shown today helps. As a general rule, it's not required for most common usage scenarios, but as we've gone through earlier, there are some cases where you need to manually consider doing it. As a general rule, except for HTTP client, it's safe to dispose of anything else, and the implementation will do whatever it needs to do. But for HTTP client, because of that reuse situation and avoiding socket exhaustion, that one's a little bit more nuanced. Hopefully that's enough information then for you to go and enjoy talking HTTP in .NET. So with that, I'm going to say thank you very much for listening. Reminder that if you have any questions or you want to reach out, you can follow me at Steve J. Gordon on Twitter. You can find more information about all of this stuff on my blog, and the link there, the bit.ly/.net-http, will take you to a link with all of the resources and slides that I've shown you that might be useful. So looking at the time, I've got a few minutes left for questions, so hopefully we can see if there's any from anyone in the room, and I'll try and do my best to answer them. Otherwise, if you're leaving now, thank you very much for coming along.